There are harbors on the American coast where you can still see them if you know where to look. The booms are down, rusted flat against the dock, or tipped into the water at an angle that tells you the thing stopped working and nobody thought it worth moving. The paint is gone. The boiler housings have opened to the weather. Some of them are half-submerged, tide-stripped to bare metal, the steel showing through in sections where the hull plate has rusted out entirely. They are the steam cranes that built the modern American harbor, and before electric hoisting equipment replaced them, they were the most dangerous machines on any waterfront in the country. The era that produced them ran roughly from 1865 to 1920. In those 55 years, American harbors were rebuilt almost from the ground up. The channel depths that existed in 1860 were not sufficient for the iron-hulled steam vessels coming into service in the 1870s and 1880s. Dredging was part of the answer. The other part was new dock construction, new seawalls, new dry docks cut from solid rock and lined with granite blocks that weighed 20 tons each. Moving those blocks, placing them, and setting them precisely in a dock wall that might run 500 feet long required lifting equipment that did not yet exist in any reliable form. The steam crane was the answer the engineers settled on. It worked. It also killed the men who ran it in ways that were not always quick. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. The men who operated steam cranes on American waterfronts in this period were a distinct trade. They were not common dock workers. They were engineers in the working-class meaning of the word, the men responsible for the operation of a steam engine. The crane engineer managed the boiler, read the pressure gauge, controlled the throttle that governed the hoisting drum, and made every judgment call about what the machine could safely lift on a given day with a given wire rope that had been in service for some number of months, that the equipment log may or may not have accurately recorded. Below him, on the dock or on the floating barge that carried a floating derrick crane, were the riggers. The rigger's job was to attach the load to the hook. On granite blockwork, this meant wrapping iron chains around a block that might weigh 15 or 20 tons, setting the chain links at the calculated balance point so the block would ride level on the hook, driving iron dogs into the stone at the lift point, and signaling the engineer to take up the slack slowly until the chains were taut and the block lifted clear of the stone bed. Getting the balance wrong was not an abstraction. A block that lifted off-center on the chains would swing as it rose. In a confined dock excavation, a swinging block had nowhere to go except into the nearest wall or into the nearest man. The riggers who worked this trade knew the physics by feel. They learned which direction a block would drift based on where the balance point sat relative to the hook. They learned it by watching blocks move and by understanding what happened when one did not move as expected. The cranes came in two main configurations. The land-based derrick crane, a guide boom fixed to a mast on the dock face, could swing through an arc and place loads at various positions along the dock wall. The floating derrick, mounted on a barge or pontoon and moored in the harbor, could reach positions that no land-based machine could access. Both ran on steam generated by a fire tube boiler, coal-fired, tended by the crane fireman whose job was to hold the working pressure near the rated limit without exceeding it. Boiler design in the 1870s and 1880s was advancing faster than inspection was. American manufacturers produced boilers rated at widely varying pressures, with varying safety valve designs and varying quality of steel plate and riveting. A boiler rated for 150 pounds per square inch of steam pressure and properly maintained would run safely for years. A boiler with a corroded plate, a sticking safety valve, or a fireman who had pushed the pressure above the rated limit because the load required more power than the engine was delivering, was a different machine entirely. Boiler explosions on construction sites and in harbors were not rare events in this era. The United States Steamboat Inspection Service, which had jurisdiction over marine steam equipment, recorded hundreds of boiler failures annually in the 1880s and 1890s. Harbor construction equipment fell partly outside the inspection service's authority, depending on how it was classified. A floating derrick barge that moved under its own power fell under one set of rules. A barge that was towed to a mooring and kept stationary during operations fell under different rules. Contractors knew which side of that line they preferred to be on. Equipment that was regularly inspected cost more to operate because inspection meant shutdown time and sometimes mandated repairs. The man who ran a harbor construction boiler was not always the man trained to do it. Formal boiler operating licenses existed by the 1890s in most states, but enforcement on construction sites was inconsistent. The demand for men who could manage steam equipment outpaced the supply of certified operators. A fireman who had learned on a stationary mill engine might find himself hired as the crane fireman on a dock construction barge because he was present and could demonstrate he knew how to light a fire and read a gauge. The gap between what he knew and what the job required would show up in the record only if something went wrong. When a boiler let go, it did not merely fail. A boiler operating at 150 pounds per square inch contained roughly the stored energy of a small artillery shell. The rupture was instantaneous. The steam that had been contained under pressure expanded to approximately 1,700 times its liquid volume in a fraction of a second. The boiler shell became shrapnel. Workers within 50 feet of the explosion were killed by the concussive wave, by the fragments, by scalding steam, or by all three at once. Workers at greater distances were struck by flying hardware. The crane structure above the boiler was lifted and thrown. Loads that had been suspended on the hook dropped. That dropping load is the buried alive part. A 20-ton granite block suspended 10 feet over a dock excavation, released without warning when the crane carrying it was destroyed by a boiler explosion, fell into whatever was below it. In an active dock construction excavation, what was below it was men. The dock excavations added their own constraints. A dry dock cut required digging a basin in the harbor bed to a depth of 30 feet or more below the waterline. The walls of such a cut were close on both sides. The working floor was wet from constant seepage, and the space directly above the workers was occupied by the crane boom and the load it carried. When the load moved, everything in the sweep zone was at risk. Foremen marked clear zones on the rock floor at the start of each shift, or tried to. A shift that started with chalk lines on dry stone had those markings obscured by midday when ground seepage ran heavy. The men learned to watch the load rather than the floor. Watching the load meant keeping your eyes up. Keeping your eyes up and your hands on a hand tool at the same time was not always possible. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. The other failure mode was the wire rope. Steam cranes of this era used wire rope hoisting lines manufactured to improving, but still imperfect standards. A new rope had a rated working load capacity that the manufacturer specified. What happened to that rating after 6 months of use in a saltwater harbor environment, wrapped around a drum that may or may not have been properly sized for the rope diameter, was a question the industry did not have reliable tools to answer. Wire rope inspection in the 1880s meant visual inspection. A foreman or rigger walked the length of the rope and looked for broken wires, kinking, bird caging, where individual strands began to splay outward from the main body, and surface corrosion. What you could see by eye told you something. What was happening inside the rope, in the core where wires corroded against each other after water had wicked through broken outer strands, was not visible from outside. A rope that looked acceptable on Tuesday morning might have been running at 60% of its rated capacity. The load that had been lifted safely on Monday might be at the edge of what the rope could hold on Wednesday. The rope gave no warning. It held, and then it did not hold. A wire rope failure under load is not a gradual process. When enough wires in a strand have failed, the remaining wires take the combined load, exceed their individual breaking strength at once, and the rope parts in a fraction of a second. A 20-ton block falling from 15 feet lands at roughly 20 miles an hour. In a dock excavation where the walls are rock and the workers are using hand tools close to the placement zone, there is no margin for reaction. The signal from the crane operator to the men below to clear the zone depended on whistle codes and hand signals, on a chain of communication that worked when everyone was paying attention and the visibility was adequate, and the noise from the boiler and the hoisting drum did not mask the warning. When any of those conditions failed, the men who had not cleared the zone were under the load when it arrived. The harbors where this work happened were spread across the country. Boston, New York, Baltimore, Philadelphia, New Orleans, San Francisco, and the Great Lakes ports all underwent major construction and improvement work in the period from 1865 to 1920. Army Corps of Engineers records from these projects are among the best documentation of the methods used, because federal harbor projects required engineering reports and completion records that private contractors were not always obligated to produce. Those records show a consistent pattern across multiple projects. Boiler failures cluster in the summer months, when heat affected available cooling water and when pressure to make daily progress ran highest. Wire rope failures follow no seasonal pattern. They happened when a rope had accumulated enough damage that the next lift was one too many, and that threshold bore no relationship to the calendar. The men who worked under the cranes had no formal way to object to the condition of the equipment above them. No safety representative existed on most harbor construction sites. Regulatory inspection of crane equipment in land-based harbor work was rare before the 1910s in most states. A rigger who refused to work under a crane he judged unsafe was a rigger who was not working. The contractor had other men at the gate that morning. What made the work possible, despite all of this, was accumulated practical knowledge. The crane engineer who had worked steam equipment for 10 years had a sense of what a boiler sounded like at proper pressure and what it sounded like when the safety valve was laboring to hold it back. The rigger who had set chains on granite block for 3 seasons knew which stone was good for driving iron dogs into and which would pull out under load. None of that knowledge was written down in any form that survives. It passed from man to man in the course of work, and when a project ended and the crew dispersed, the knowledge went with them. The projects did not always end cleanly. A harbor improvement, funded by a congressional appropriation, ran until the money ran out, and then stopped until the next appropriation cleared. Crews were released. Equipment sat at the mooring in the salt air. When funding resumed, a new crew assembled from available men put back into service a machine that had been sitting idle for a year or two, run by workers who had not operated it before and had no one to tell them what to watch for. Army Corps construction diaries from the 1890s occasionally note the condition of equipment returned to service after such gaps. The entries are brief. Boiler needs retubing, wire rope replaced, boom showing rust at heel joint. Those are the problems the resident engineer noticed. They do not represent everything that was wrong. The electric overhead crane replaced them starting in the 1910s. Electric hoisting offered consistent power without the boiler maintenance requirement, without the boiler explosion risk, and without the need to maintain a coal supply on the barge. By 1925, new harbor construction projects in American ports were using electric equipment almost exclusively. The steam cranes that were still running were retired as they wore out, and when they wore out, in a position where moving them was inconvenient, they were left where they stopped. The cranes sitting in the tidal zone today survived past their working lives for a simple reason. Moving a derelict steel structure that weighs 20 or 30 tons and sits at the edge of a working waterfront costs money. If the structure is not in the way, it stays. Water gets into the boiler casing. The boom rusts through at the heel joint. The wire rope becomes a hanging mass of individual corroded wires. The whole thing sits in the tide, going out and coming back, and the steel gives itself back to the water, 1 year at a time. Some of them have been doing that for 100 years. If you find one of the old machines now, you are looking at a structure that ran on fire and pressure and the judgment of men who were not always given adequate information about whether what they were running was safe to run. The harbor it helped build is still there. The dock walls the cranes placed block by block are still holding back the water. The cranes are not on any registry. No plaque names them. They are in the tidal zone, because the tidal zone is where they stopped. The block is still in the dock wall. The wall is still standing. The crane that placed it is rusting into the harbor floor not far from where it set that block for the last time. The water covers it at high tide and uncovers it at low. The men who ran it are in the project ledgers as crew numbers, when they are in the record at all. The accident reports give initials in some cases, full names in others, and in a substantial number of cases, only the description of what happened, the date, and the number of hours the site was shut down while the area was cleared. What happened to the man who left the site that day and did not come back is not in those records. The machine is in the water, the wall is standing. That is what the record shows. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.